Welcome to Kinetics class number 2. Just a quick note before we get started. You probably will have gotten an email about this before you see this video, but just a quick reminder, please do not pay attention to your grade total on Canvas. It's not at all properly weighted and it's not kept up to date necessarily. And also, I'm trying some new things in our online situation, and am definitely going to do some modification of how the grading is done. So just a reminder, you get pretty high participation credit for going through the interactive classes. And if you're getting lower grades because of getting things wrong, don't worry about that. It's the learning experience at this point, and those grades will be adjusted. So please just ignore your Canvas grades for the moment. I will try to do as well as I can to get some kind of more accurate grades available to you soon. Okay, so let's pick up where we left off last time from the first kinetics class, and we had started doing some calculations with various reactions for times and concentrations. How long does it take for the concentration to change to a certain amount, or what's the concentration after a certain amount of time has passed? And these are things that can be done pretty much just by plugging into the appropriate equations. So here's question 5. We have a reaction and a temperature. We have a rate law and a rate constant. Do note this is a second order rate law, and the rate constant's units reflect that it's second order. And question A is starting with a certain concentration of NO2. What's the concentration after 5 minutes? So I'm going to embed a question here for you to pause, try to work out the answer, and see how well you do on that. And the quick note that it's second order. If you don't remember the equation for the relationship between concentration and time for second order, look back in your notes from either previous class or the screencasts, and you should be able to find the appropriate equation, and you're going to know all of the quantities needed other than the concentration at the 5-minute elapsed time. So you should be able to plug in all the values that you are given and then do the algebra to solve for it. So I'll pause here for a question, try to work the answer out, and then we'll go through the answer. Okay, so let's see how you did. It's a second order rate law, so the relationship between concentration and time is as shown. 1 over concentration of NO2 at time t is the rate constant K times the time that has elapsed, plus the 1 over concentration of NO2 initial, or NO2 naught. So we plug in the values that we know. K is 0.543 per molar per second. The time is 5 minutes, but I changed it here to 300 seconds because we need to have our units for time be the same. Seconds and per second we need to cancel. And then our initial concentration was 0.0296 molar, and we have 1 over 0.0296 molar. Now note, this whole quantity, when you calculate it out, is going to equal 1 over NO2 at concentration at time t. So I got 163 for this number and 33.8 for this number. And so the quantity is the sum of 163 plus 33.8, and then that is equal to 1 over NO2 at time t. So then we have to take 1 over this value, and here I have it written as to the -1 power. That's the same as the reciprocal, or 1 over it, is equal to NO2 at time t. And when you do that math, you get 0.00508 molar, and then check and see if this seems reasonable. If we start with 0.0296 molar, as time progresses, we'd expect the concentration to go down, and so we better get a value that is at least a little, maybe significantly smaller than 0.0296 molar, which we do. 0.00508 molar is the concentration after 5 minutes has elapsed. using the second order time versus concentration relationship. Okay, part B, same equation, same rate law, or same reaction, same rate law, starting with the same initial concentration. Now the question is, how long does it take until the NO2 concentration reaches this value, 0.0124 molar? So hopefully you'll say, oh, I know what the relationship is mathematically that I use, substitute values in, but now we're solving for time, how long it takes. So I'm going to insert a question here, pause the video, and so try to work out the correct answer to this, and then we'll come back and check and see how well you did. Okay, so as noted before, same rate law, second order for the same reaction. So the same time versus concentration relationship, 1 over NO2 at time t equals K times the time plus 1 over NO2 concentration initially. And now we know everything except the t value. So here I'm doing rather than just plugging in numbers, I'm actually doing the sort of algebra to solve for t. So to get t by itself, first you subtract 1 over NO2 at time 0 from both sides. So subtract this from that, 1 over NO2 at time t minus 1 over NO2 at time initial or time 0. That will then equal KT. And so then to solve for t, I divide both sides by k, which is the same as multiplying by 1 over k. Don't forget your parentheses around this whole grouping of 1 over NO2 at time t minus 1 over NO2 at time 0. And then that gets multiplied by 1 over k. Now I'm going to plug in the values. K is 0.543 per molar per second, and it's 1 over that. 1 over 0.0124 is the at time t concentration. Notice this is not the initial, this is the final concentration. And then minus 1 over 0.0296 molar, that was the initial concentration. The molarities are both in the denominator here, so that's per molarity. Those will cancel with a 1 over per molarity, and that'll leave us with 1 over seconds, which is seconds for our units. And plugging in the values, you get 86.3 seconds for the time that has elapsed for the concentration to change to that value. Okay, now we're going to take a look at some graphical analysis, and we've seen this before, so there's a bit of a recap here. If we have simple reactions where some substance, let's say A, makes products, and we look at them graphically, again, we have 3 choices we're considering in our little constrained universe for Chem 1B, 0th order, 1st order, and 2nd order. If it's 0th order, the rate is rate equals K times A to the 0 power. The time versus concentration relationship for 0th order, only for 0th order, is concentration at time t equals negative K times the time plus the concentration initial. And we can look at this, and we've seen this before a few times, and you saw it in the iodine clock reaction lab. This is like a y equals mx plus b relationship, a straight line, where our y is the concentration of A at time t, our k, or our m is the rate constant k, but negative, our x is the time, and our y-intercept is the initial concentration of A naught. So if we graph this, A versus t, concentration of A versus time, we get a straight line with a negative slope, and the slope of that line is equal to the negative of the rate constant. So graph of concentration versus time is a linear graph, and that, sorry, I should back up just a second. So if we know that it's 0th order, then we know this is what's going to happen. If we don't know what the order is, we can graph A versus T, and if we do get a straight line, then that tells us the reaction is 0th order with K equal negative slope. So sort of 2 cases, you could know it's 0th order and you know the graph's going to end up being linear, or you could not know its order and you could do the graph, and if you find it's linear, then that tells you that the reaction was 0th order, so you've now figured out the rate law because you figured out the order and the rate constant. And then the same basic idea applies for first order and second order. If it's a first order rate law, then rate equals k times a to the first power. That mathematically can be shown to have a concentration versus time relationship of a at time t equals a at time 0, a naught, times e to the minus kt. And if we take the natural log of both sides, we get ln of a at time t equals negative k times t plus ln of a at time 0. And this also is a straight line relationship. If our y is ln of a at time t, our slope, our m, is negative k, our x is time, and our y-intercept b is ln of a at time 0. So if we know it's first order, we know we're going to get a straight line graph. If we graph ln of a versus t, we'll end up getting a straight line graph with a slope of negative k. And as noted, it also means if we don't know the order of the reaction and we end up graphing ln of a versus t and that turns out to be straight, turns out to be linear, then that means the reaction is first order and we have the rate constant equals the negative value of the slope. And quick note, the slope will be a negative, so the negative of a negative slope will be a positive value, and rate constants are always positive. So if we do this graphing and find this relationship, then we know the rate law because we found that it's first order and we found the value of the slope. And then same idea applies for second order. If it's a second order rate law, rate equals k times a concentration to the second power. That gives us a concentration versus time relationship of 1 over a at time t equals k times t plus 1 over a at time 0. This is also a y equals mx plus b linear relationship if our y is 1 over a at time t, if our slope m is k, positive k this time, if our x is t, and if our y-intercept b is 1 over a at time 0. So if we know we have a second order rate law, then we know if we graph 1 over concentration of a versus time, we'll get a straight line. This time it's sloping positively, and the slope of that straight line will be positive k. And of course, what this also means is if we have some time and concentration data and we don't know the rate law, if we graph 1 over concentration versus time and that turns out to be linear, then we know the reaction is second order, and we know that the rate constant will be whatever the slope is. And so that's kind of a recap of stuff you've already seen. Now we're going to do an example and grind all the way through it for some practice. But as a note, the typical thing that's done now is we often collect concentration versus time data for a reaction we don't know the rate law for, and then we just make all three graphs. We make the concentration versus time graph, ln concentration versus time graph, and 1 over concentration versus time graph, and see which one is linear. One of them will be straight or the straightest. The other two will be curved, and the one that's straight will tell us whether we have 0th order, first order, or second order rate law, and will give us the value of the rate constant. Therefore, we'll know the whole rate law. We've done this before a couple times as well. I'll just quickly remind you, you're going to have to know how to do this kind of graphing on your calculator by the time we have our next examination. Most calculators have some sort of a stat function for where you enter your data. So you enter your data in lists, your x values and your y values. Make sure you don't get them backwards. You make the graph, and I strongly suggest taking a look at the graph just visibly. That often tells you whether the graph is potentially straight or if it's distinctly curved. So I'd highly recommend actually making the graph and looking at the shape. And then if it is linear or has a chance of being linear, do the linear regression to find the slope. So let's do it with an example. So question 6, the disaccharide sucrose reacts in dilute acid solutions to form the monosaccharides glucose and fructose. So you may be aware sucrose is actually glucose bonded to or combined with fructose. These two monosaccharides make the disaccharide, and you can split the disaccharide into its two components in an acid solution. And here is some data that was collected for this reaction of sucrose in hydrochloric acid. And we have time, 0 minutes, 50 minutes, 100 minutes, 150, 200 minutes, and then the concentration. And you can see the concentration is decreasing from 0.400 molar and gradually going down. So we have concentration versus time data. We should be able to graph it and determine the rate law. Again, think about what you should be doing. You should be graphing concentration versus time and seeing if that's straight. And if it is straight, that'll tell you that it's 0th order. And you should try graphing ln of concentration versus time. And if that's straight, it'll tell you it's 1st order. And you should try graphing 1 over concentration versus time. And if that's straight, that'll tell you it is 2nd order. So give that a try, and we'll embed a question here, and then we'll come back and work through all the details. Okay, so here we're back at our question with our data, and this is the first thing that I tried. I tried graphing concentration versus time, and my graph looked kind of like that. And if this is straight, then we could say that this is 0th order. But if we put a straight line next to our data is distinctly curved. And in fact, you can look at your data. We're going every 50 minutes, so that's a regular increase of 50 minutes. And we go from 0.4 to 0.333 to 0.277 to 0.231 to 0.192. And you might notice that this difference compared to the next difference compared to the next difference, those are not constant differences. So this shouldn't be, you shouldn't expect this to be linear. It looks curved. And if it's curved, that means this is not a 0th order reaction. And that means it's either 1st or 2nd order, and we're going to have to try those. Okay, to find 1st order, we leave the time alone, but we're going to need to take the ln, the natural log of the concentrations. So ln of 0.4 is negative 0.916. Ln of 0.333 is negative 1.100. Ln of 0.277 is negative 1.284, etc. for the next two. And you could look at these differences and see if they look like they're fairly consistent, fairly regular. And you can graph ln of concentration versus time. And here's what my graph looked like. And I'm going to say that looks pretty straight. And I did the linear regression, and I got a slope of negative 0.0037, y-intercept of 0.9164, which I don't, negative 0.9164, which I actually don't care about. That's not useful information right now. And then I got a correlation, an r-squared, of essentially 1. So this looks really, really straight with a negative slope. And that's linear, which means we have a 1st order rate law. And 1st order rate law is rate equals K times concentration of sucrose to the 1st power with our rate constant of 0.0037. And actually, I'm giving it to 3 sig figs. 0.00367 is our rate constant, and the units are per minute because we did our times in minutes. So that is the rate law. And then just as a note, we nominally, we have a straight line, so it's 1st order. That means it can't be 2nd order. But if you have the time and the inclination, it's not a bad idea to just graph the potential 1 over concentration for 2nd order. It just kind of gives you clarity that you were in fact correct. And if I graph 1 over concentration versus time, I get a curved line. It's distinctly not straight, and that just confirms that it is not 2nd order. Okay, so Generally speaking, you try 0th order, then you try 1st order, then you try 2nd order. If you have enough time, try all of them for confirmation. But once you get one that is straight, then you've answered the question. Do note, book data is often kind of idealized, and you get a really, really clear-cut determination of which line is straight. In the real world, often there's some, it's just harder to tell. You have some data that has more associated uncertainty, and so sometimes it's a close call between 1st order and 2nd order, let's say, as to which is straighter, and sometimes you have to do further analysis to convincingly determine what the order is. But most of the time in an actual academic class, when you're learning this, you'll get kind of idealized data where the determination is really clear cut. It's distinctly one order, not either of the other two. Okay, now kind of moving away a little bit from time versus concentration calculations and taking a look at what's going on at a molecular level. On a molecular level, what has to happen for any reaction to occur? But we'll look at the reaction here of A, which is a purple sphere, reacting with BC, where B is a green sphere and C is a sort of yellowish sphere. So these represent, let's say, atoms that are or molecules, and for these to react, well, for A and BC to react to make A, B, and C, first of all, the molecules actually have to contact each other. They have to collide, and it turns out they actually have to collide with the right orientation. So if A plus BC makes A, B, and C, we actually have to get A and B physically hitting each other. If the A hits the C, that's not going to make A and B bond together. A has to hit B to make A and B bond together. So they have to collide. They have to collide with the right orientation, and they have to hit hard enough. They have to hit with enough energy to overcome something called an activation energy barrier. So this is kind of like if you're driving, in a parking lot slowly and you collide with another car. If you're both going 2 miles an hour, you just kind of touch bumpers, you just bounce off of each other, scratch a little paint maybe, but no damage done, nothing really changes. But if you're driving fast and you hit another car, then you can collide with enough energy to rearrange your car and rearrange the other person's car, and in the analogy here, make new stuff, make new molecules. So you have to hit hard enough with enough energy to make some bond break and new bonds form. Like that. Want to see it again? So they hit together, and then A and B stick together, and C separates off by itself. Okay, now most reactions aren't quite this simple, but that principle applies. And here's what the graph of this looks like. Our standard graph we've seen a number of times now of reaction profile. So reactants moving to products from left to right. Energy vertically from low energy to high energy. And so here the reactants have a certain energy. They have to go over this activation energy barrier, and if they make it to the top of this activation energy barrier, if they have at least this much energy of collision, then that's sufficient energy to make the reaction now go downhill to products. And so the height of this hill from the reactant's potential energy to the top of the activation energy barrier, that's what's called the activation energy, and that's what has to be overcome for the reaction to happen. Now, hopefully you would say, what factors are going to affect this besides type of reaction? So of course, for a specific reaction, there's a specific activation, specific activation energy. And you would probably say, well, you know what? I bet temperature plays a role. If we change the temperature, the molecules have more energy or less energy, and that's going to change our rate, of course. And if we increase the temperature, we tend to get faster reactions. And we get faster reactions because more of the molecules have enough energy in their own kinetic energy and in the energy of their collisions to overcome, so to speak, the activation energy. And this is not a thing we're going to derive. This is just a known relationship that will be provided as an equation for you, but you're going to need to know what things mean and how to deal with it. It turns out that the rate constant K depends upon temperature and on activation energy according to this equation. K equals A times E to the negative E sub A over RT, where this E is the base of the natural logarithm, the number. The capital E sub A is the activation energy, and then this whole quantity, negative E sub A over RT, all of that is in the numerator, so that's like in parentheses. So A is what's called a frequency factor. It has to do with what it kind of sounds like, frequency of collisions, and the frequency of collisions with the proper orientation for reaction. This is something we could look into in detail, but in this class, we're going to pretty much ignore it. For us, it's a constant for a given reaction, and we'll just note it's a thing, and we won't calculate anything about it. We will calculate activation energy, and then R is our usual gas constant, and we have to use the joules value, and then T, of course, is our temperature, and we, of course, have to use temperatures in Kelvin. Okay, now we can do a number of things with this, and one of them is to linearize it. So we've already done linearization. We did this for determining rate laws. That was the graphical stuff we did. We found what the linear form was for each 0th, 1st, and 2nd order rate laws. We can do the same thing for the rate constant activation energy equation, the Arrhenius equation. And if you take the natural log of both sides of this equation and then do a little bit of rearranging, you get the following. ln of k equals negative E sub A over R times 1 over T plus ln of A. And, again, this is a little bit of a review seen in a screencast already. This is a straight line, y equals mx plus b. So you're probably noting we do this a lot. This is a straight line. There's only one way you can have a straight line. There's lots of ways you can have curved lines, and that's why we like to linearize things, because then we kind of definitively establish relationships. And so in this case, y is ln of k, x is 1 over t, the slope m is negative E sub A over r, and then the y-intercept b is ln of a. And so this might sound suspiciously like something we just did. We graph one thing versus another thing. It gives us a straight line with a slope that allows us to determine something of interest. So we're going to graph ln of k, that's your y value, versus 1 over t, those are your x values, and that will give a straight line with a slope of negative E sub A over r. And since r, of course, is a known constant, this allows us to determine the activation energy E sub A. So this is another thing you'll need to know how to do, and we'll do a practice problem with it next. Be able to take temperature. Notice this is capital T for temperature, not lowercase t for time. So temperature versus rate constant data. Graph them in the appropriate way. Get the slope of the line from that graph, and that allows us to determine the activation energy value E sub A, which is a constant for a given reaction. Note also that this is going to be the heart of the next lab that we're going to do, and for better, worse, or indifferent, it's not going to be a lab simulation. Hopefully, it's going to be one where Susan and I video the lab procedure itself and the data, and you'll make some observations. You won't get to do the fun mixing of stuff in test tubes, but you will get to watch the color change and time how long it takes, and then do some calculations and determine an E sub A. So this is going to be the heart of some homework questions. You can probably expect a test question on it, and it'll be a lab as well. Okay, so same graphing stuff as before. Enter your data. You're going to need to know how to do this in your calculator. Graph 1 over t, x values, versus ln of k, y values. You'll get a straight line. It'll have, straight line. It'll have a negative slope, and the slope will equal the negative of E sub A over R. Now, here is a question that gives you a chance to determine the activation energy for a given reaction, where we have a reaction and we have temperature versus rate constant data. So give it a try. Graph the appropriate things as your x and your y. Get the straight line, get the slope, use the slope to calculate activation energy, and enter your answer. And then we will go over the question in the usual manner. All right, so here is the data that were given originally, temperatures in degrees Celsius, and then the rate constant has units of molarity to the -1 times seconds to the -1. And to determine an activation energy, we know that we should be graphing 1 over temperature, where the temperature has to be in Kelvin, versus ln, natural log of the rate constant K. And so make sure you add 273 to each of these temperatures to get its temperature in Kelvin, and then take 1 over it. Here are the values I got for that. Note, of course, that the 1 over temperature values are typically quite small, and do be careful about significant figures. If you round these numbers off too much, like if you rounded this temperature off to 0.002 instead of 0.00180, that will give you some very poor results for your graph and your slope. The natural log of the rate constants very often are negative numbers, and so again, be careful with those having enough significant figures. And then use your calculator in the appropriate way to graph 1 over t, which is your x, versus ln of k, which is your y. You should get a straight line, which has a negative slope, and I got a slope of negative 21,800. And then remember that the slope, in this case negative 21,800, is equal to negative E sub A over R. And so we want to solve for E sub A. We know the slope, we know the value of R. So here are the numbers, plugging it in, negative 21,800 Kelvin. The slope has units of Kelvin, equals negative E sub A over R, which is 8.314 joules per Kelvin. Notice the kelvins are going to end up canceling now. When you solve for E sub A, you get rid of the negative signs, and you also cancel out the Kelvin. That ends up giving you 181,000 joules. And this is pretty typical. Typically, activation energies are tens to hundreds of thousands of joules. And since they're big enough in joules, it's pretty conventional to convert them to kilojoules. So this would be reported as activation energy of 181 kilojoules. And also note, sometimes it's done as kilojoules, sometimes as kilojoules per mole, where remember the per mole means per mole according to the stoichiometry of the reaction. So for this reaction, it would be 181 kilojoules per 2 moles of HI, or per 1 mole of H2, or per 1 mole of I2. So both are done as units, kilojoules or kilojoules per mole, with kind of remembering how the per mole is done on the basis of the reaction and its stoichiometry. All right, so we've dealt with activation energy, how to determine it from temperature rate constant data. Now let's take a look just kind of conceptually at what these potential energy profiles look like for reactions, where we now incorporate activation energy and enthalpy change for the reaction. So give this a try. Here is our x-axis reaction coordinate as we move on the left from reactants to the right as products, and vertically energy is going up, And so high potential energy at the top, lower potential energy at the bottom. So see if you can sketch what the potential energy profile for this reaction would look like given the E sub A and delta H shown. And just as a note on this graph, these divisions were meant to represent 25 kilojoules per mole for each of these gaps. So that's just to kind of make it, or each from one dotted line to the next. So that's just kind of a way to scale things properly. So give that a try, see what your graph would look like, and then we'll go over the answer. And hopefully you did something that looks like this. The reactants have a certain energy, and it's just a starting point. I chose here just to make everything fit on the graph nicely. You could have started on this dotted line, and then everything would be shifted downwards a little bit from what I did. But we have a reactant energy of whatever it is. Then the E sub A, the height of this energy barrier, this hill, is 75 kilojoules per mole. So that's, if each of these dotted line spacings is 25 kilojoules, then 25, 50, 75 kilojoules, that's the height of the hill. And then the delta H is a negative number, and the delta H is the difference in energy between the reactants and the products. And since the delta H is a negative number, that means the reaction is exothermic, gives off heat, and so the products are lower in energy than the reactants, and they're lower in energy than the reactants by 100 kilojoules or 100 kilojoules per mole. So that's the potential energy profile, and those are the values that let you make it to scale. We've already kind of gone through this, label the reactants, products, and the transition state. Well, I guess we did at least some of it. Those are the reactants. The products are what we end up with. And then the transition state is what is gone through as we move from reactants to products. In the transition state, you have a full transition state at the top of the activation energy hill. And then what's the activation energy for the reverse reaction? So if we're starting here with the quote-unquote products and now moving in reverse to what used to be thought of as the reactants, what's the activation energy? So see if you can figure out what that would be and enter the answer, and then we'll go over it. And the activation energy going forward is 75 kilojoules. The difference in energy between the reactants and products is 100 kilojoules. And so if we're going backwards from the reactants energy to the top of the hill, which you have to overcome, that's the activation energy going in reverse. And so that total is 175 kilojoules. So the activation energy for the reverse reaction is that, 175 kilojoules. Okay, now here is a second reaction. And for comparison, we have the first reaction's energy profile shown. And so on the same scale, and let's just use the same starting point as well, reaction 2 has E sub A is 50 kilojoules per mole, and delta H for the reaction is negative 150 kilojoules per mole. See if you can draw the energy profile for that, and then we'll answer a couple questions. And hopefully you drew something that looks kind of like that. So starting at the same energy, that's just sort of for comparison purposes. The energy hill going forward is 50 kilojoules. So notice that's a smaller activation energy than for reaction 1. And then delta H is negative 150, so that's also an exothermic reaction. And from the reactants to the products, that difference of 150 kilojoules is a bigger difference between reactants and products in terms of energy than for reaction 1. So that's what the reaction energy profile looks like for reaction 2. And now a couple questions. Which reaction has the faster forward reaction at a given temperature? And see if you can have an answer to that and a reason why. And hopefully what you said is, well, reaction 1 has an activation energy of 75 kilojoules. Reaction 2 has an activation energy of 50 kilojoules. The lower activation energy is easier to get past. More molecules have enough energy to overcome the 50 kilojoule per mole barrier than the 75 kilojoule per mole barrier. That means more molecules will react, and therefore we will have a faster reaction, at least going forward from left to right. So reaction 2 has the faster forward reaction. Okay, what about which reaction, 1 or 2, has the faster backward reaction? So again, see if you can come up with your answer and your reasoning, and then we'll go over it. And hopefully what you said is, well, going backwards, reaction 1 has a 175 kilojoule activation energy hill. Starting with stuff on the right, moving to stuff on the left, we have a 175 kilojoule hill to climb. For reaction 2, that hill is 200 kilojoules. We have 150 kilojoules per mole for the delta H, and then another 50 kilojoules per mole for the activation energy. That's a total of 200 kilojoules per mole. And so in this case, reaction 1 has the smaller hill to climb going quote-unquote backwards. Do note it's a much bigger hill than either of the forward reactions had, and so the faster backwards reaction will be reaction 1 because it has a smaller activation energy than reaction 2, and therefore more molecules have enough energy to overcome that. Also note that both backward reactions will be much, much slower than the forward reactions because both of the backwards reactions have much, much higher activation energies, and that might give you reason to believe, which of course is true, that the position of equilibrium is kind of likely to fall on the product side. And here is just sort of a generic summary of this. Activation of a forward reaction compared to activation of a reverse reaction, reactants versus products, delta H, and then a quick note, the transition state is often also called an activated complex. And so this is the generic activation energy profile for a reaction. All right, now last thing for this class is to observe the effect of a catalyst. And normally I'd like to do this in person, but here we're going to have to rely on a video. And so this is a video from the Royal Society of Chemistry showing actually a number of different catalysts catalyzing a hydrogen peroxide decomposition reaction. So let's take a look at that.
Line up 6 large cylinders and add catalyst to them as follows: half a gram of manganese dioxide, half a gram of lead dioxide, half a gram of iron oxide, a small amount of chopped potato, a small amount of chopped liver, and a small amount of chopped boiled liver. It needs to be boiled in water for about 5 minutes. To each of these, add 1 centimetre cubed of washing up liquid. It doesn't need to be measured accurately, but you need to use the same amount each time to ensure that it's a fair test. Avoid spilling the washing up liquid down the sides of the tube. And indeed the catalyst also needs to be at the bottom of the tube and not down the sides. Then simultaneously add 25 centimetres cubed of 75 vol hydrogen peroxide to each of the cylinders. The foam will rise up the cylinders at widely differing rates. The foam is formed from oxygen, which is produced by the decomposition of the peroxide. The rates at which they rise up the cylinders give a graphic comparison of the differing effectiveness of the catalysts. The order is normally lead dioxide, manganese dioxide, fresh liver, potato, iron oxide, and then boiled liver, but this may be affected by the surface area of the powders. Liver contains a peroxidase enzyme which is denatured by boiling it. It is usually possible to light a glowing splint in the foam, although sometimes this fails if there's too much water in the foam.
And now let's just note that what a catalyst does is it makes a reaction go faster. So all of the catalysts you just saw made the decomposition of hydrogen peroxide reaction go faster. It speeds up a reaction. And the important thing to note is a catalyst does this without being consumed. So the catalyst is used to speed up one set of molecules reacting, then it's used again to speed up another set or facilitate the process of another set of molecules reacting. And so it keeps on getting reused, and it isn't used up by the reaction. And that's really important, especially for biochemical processes, because we have all kinds of things going on in our bodies in terms of respiration and digestion and just everything that makes us work, where we can't afford to have molecules that speed up reactions be used up, because then we constantly have to be producing those molecules. So catalysts, it's very important that they aren't used up in the process, and we also of course need these reactions to go quickly. And we'll explore this in a little more detail in the last kinetics class, but worth noting that what the catalyst does to speed up the reaction is it lowers the activation energy. Now specifically, it provides a different reaction pathway that has a lower activation energy, and if it lowers the activation energy, then of course the reaction goes faster. And it turns out you don't have to lower the activation energy that much to really have a significant speeding up effect on reactions. And catalysts often speed up reactions by factors of tens, hundreds of thousands, millions, tens of millions of times faster than without the catalyst. And that is it for Chemical Kinetics class number 2.